Well, we have atmospheric pressure. Okay, our Earth is surrounded by an atmosphere of air, and that exerts an atmospheric pressure on us, and that pressure varies. It varies when you go to different elevations, but there are also variations due to weather. And if you've ever watched the weatherman, you say, well, there's a high pressure front coming through, or there's a low pressure front. And so differences in pressure in the atmosphere are what drive our weather. High pressure usually means clear weather. Low pressure is generally unstable weather. And so that's why people, get a little obsessed with the barometer. It's like, well, is the barometric pressure, the atmospheric pressure, is it going up? Is it going down? That can help us predict the weather. Altitude varies, causes pressure to vary. When you go up, high up into the mountains, my son went up to Grant Grove over the weekend. You go up there, the atmospheric pressure is less because you're farther from the main surface of the Earth. There's fewer gas particles up there because the atmosphere gets thinner and thinner as you move away from the Earth. And so the pressure decreases with increasing altitude. So I mentioned earlier, the pressure exerted by a gas is going to depend on the number of gas particles in a given volume. So here we have two mason jars. This one has more particles in it, and this one has fewer particles in it. And just like kindergartners running around a classroom, there's more pressure here. If these were children, there'd be more boo-boos, right? And this is lower pressure. There's a lower force per unit area, and thus the pressure is lower. Air pressure explains why your ears pop. You go up to Grant Grove, you experience a significant elevation change. You ride in an airplane, there are pressure changes when you go up and down, and that causes your ears to pop. Your ear has an eardrum that separates your outer ear from your inner ear. And here's a blown up illustration here. So if we go higher in elevation, the outside pressure gets reduced, and that causes the eardrum to bulge outward because the pressure in this inner part of your ear is the same, and that causes the eardrum to bulge outward. So what's popping when you hear that sound? Is it your eardrum rupturing? No. You have a eustachian tube that goes down into your neck, and normally that's mostly closed, but when pressure builds up like this, then it'll let the pressure out. And that's why yawning helps, or chewing gum, because when you yawn, you help to open up that area where the eustachian tubes are. When you come back down from the mountains, now you've got pressure on the outside that's higher and pressure on the inside that's lower, and your eardrum bulges inward. And a lot of times that's more bothersome than the other way around and harder to get to clear out as well. And that's why babies scream on airplanes. They don't do it just to torture you. Well, how do we measure atmospheric pressure? There are lots of pressure gauges out there. We're going to talk about the original one because it's much easier to understand and it illustrates the concepts better. So a mercury barometer. A mercury barometer, very simple one, can be made by taking a long glass tube full of mercury. Mercury is used because it's a liquid at room temperature and it's also very dense. So you take a tube full of liquid mercury and you invert it into a dish of mercury. Now, if you did this with water, say a long test tube or even like a burette, the water would completely stay inside the tube. It would not come down. But mercury is much more dense, and so we'll see the mercury begin to fall out of the tube, but what's left up here is a vacuum. The reason it doesn't all come out is because there's atmospheric pressure pushing down on the mercury in the dish, which is supporting the mercury inside the tube. If there were no pressure out here, all the mercury would come out. So normal atmospheric pressure will support a column of mercury that's 760 millimeters in height. That's equivalent to 29.92 inches. So, it's a significant length. So we have this unit of pressure called the millimeter of mercury. That sounds like a very strange pressure unit. It's a length of an element? What is that? Well, it comes from the Mercury Barometer. It's the height in millimeters of a column of mercury. And it's literally 760 millimeters tall. If the external pressure is higher, pushing down harder on this, it will support the column a little higher. And so the mercury barometers, as the pressure outside increases, the mercury column rises. If the barometric pressure decreases, the column of mercury begins to fall and is shorter. Millimeter of mercury, weird unit. We have another unit, the torr. The torr is just a different name for the millimeter of mercury. Torr is named after Torricelli, who was the one who first did experiments and things with the mercury barometer. Any questions? There are other units of pressure. Pascal is the SI unit of pressure. We don't use that in chemistry much. Pounds per square inch you might be familiar with if you've ever put air in the tires of your bicycle or your car. That's abbreviated PSI for pounds square inch, pounds per square inch. Average pressure at sea level is 14.7 PSI. The torr, 760 is exact. Atmospheric pressure is defined as 760, and so this is an exact number. In inches of mercury, which is abbreviated INHG, 29.92. And then we often use a unit called the atmosphere, abbreviated ATM. You can't get any money out of it. 1 ATM is 1 atmosphere of pressure. So we can use a table like this to convert between different temperature conversions or temperature units. The ones you need to memorize is 760 torr and 1 atmosphere. You need to know that 1 atmosphere is equal to 760 torr, which is 760 millimeters of mercury. The way this table is set up, all of these things are equal to each other. And so the nice thing about temperature conversions is you can usually do them in one step. So your local weather report announces that the barometric pressure is 30.44 inches of mercury. Convert this pressure to PSI. And here we have a common way of giving those relationships. 1 atmosphere is equal to 760 torr, which equals 760 millimeters of mercury. It also equals that many pascals, that many PSI, and this many inches of mercury. So what we can do is we can just start with our 30.44 inches of mercury. And we can do this in one step. We want PSI, so we put PSI on top. And we want to get rid of inches of mercury, so we put that on the bottom. Then we go look at the table. Well, 14.7 psi is equal to 29.92 inches of mercury. Each of these quantities is equal to each other. So you just pick out the 2 that you need and put them into your equation. So I've got 14.7 and 29.92. 30.44 times 14.7 divided by 29.92. This is unfortunate that it's just 14.7. They actually know it to more digits than that, but this is not an exact number, 14.7. So here, this is going to limit the number of sig figs in our answer, which is not ideal. My calculator is saying 14.955 and some other stuff. That's going to round to 15.0 psi.
If those are conversion factors, wouldn't we just stick to the first unit thing instead of sticking to the sig figs of the conversion factors?
Well, yeah, the question is, because these are conversion factors, don't we just ignore those and stay with our initial measurement? Normally, that's how it works. But this 14.7 is not an exact number. I happen to know that it's actually 14.69, and I should really change these slides to reflect that, but that's what they have in your book. So probably a good idea is if you see that the conversion factor you're using is going to limit the sig figs in your answer, you should probably look at a different resource and find a more precise value for that. Yeah, it's a good question. Any other questions? So barometer measures atmospheric pressure. A manometer measures the pressure of a gas inside of a container. And this involves a U-shaped tube partially filled with a liquid. Often it will be mercury, but it could be something else. And this tube is open to the atmosphere on one side, and it's connected to the container with the pressurized gas on the other side. And so if both of these sides of this U-tube were open to the atmosphere, what would we expect the levels to be on each side? They'd be equal, right? The liquid would sink to the bottom, and we'd see that the levels would be equal. They'd probably be in the middle here somewhere. But they're not. This side is pushed down, and this side is up. That tells us that the pressure inside this container is greater than the pressure outside. And the difference we can measure with a ruler and just measure the difference in the heights. If this is mercury, then this difference in pressure will be in millimeters of mercury. And so the pressure inside is the same as the pressure outside plus the difference. Any questions? This is a very old-fashioned way of measuring pressure, but it's very, very simple. You didn't need technology. They were doing experiments with this before we had electricity. They didn't have fancy measuring devices. But a piece of glass that you could bend into a U and some mercury and a ruler, and you're good to go. Of course, they didn't realize that mercury was so toxic in those days. It's unfortunate.